All right. Today's lecture, okay? Come on, man. Okay, come on. Ladies and gentlemen, we are coming to the end of the semester, okay? Now, it's not just we are coming to the end of this semester, okay? This is the third year of your university education. So it's already more than half, okay, of your 4 years career in this university, okay? And probably then the next semester, you have to start to plan what you will want to do after you're graduating from our school, okay? Do you want to apply for graduate school, or do you want to go directly into industry, looking for jobs and start to develop your career, okay? Whatever you want to do, I think I cannot give you any guideline. I cannot tell you which is the best. But I certainly hope that if you know, one thing is very important, that is, you know what you want. Okay, you know what you want, and you know where is your, not desire, okay, what you are enthusiastic about, what can make you feel motivated and excited. All right, okay, all right, okay. Let's go back to where we were, okay? Now, let's assume this is the output arrow, which happens to be a constant. And let's assume the purple line here represents the noise. And somehow the noise contaminated the signal. So the output arrow that is being sent to the controller look like this, okay? Now, for proportional control, it doesn't matter that much, okay? Why? Because the value of the purple and black lines are pretty much the same, okay? Maybe 1%, 2% difference. It doesn't matter that much. For integral control, it doesn't matter that much either, because integral means area under the curve, okay? Since the noise can be negative or positive, okay? So in the long run, they will, after integration, they will cancel out with themselves. So it really doesn't matter that much. But for derivative control, the story is entirely different. Because if I take derivative, what I will get is slope, right? And it depends on where do I take the derivative. If I take the derivative here, the slope is this. If I take the derivative here, then the slope is this. If I take the derivative here, then the slope is this, right? Why is that the case? Okay, the noise itself is very, very small. But after acting the noise, okay, the slope of the output contaminated output arrow becomes very, very oscillatory. And when I say oscillatory, it is a pattern in the time domain. But if you go to the frequency domain, it explains, this figure explains everything. It magnifies the high frequency components of the signal. That is what differentiated does. So be careful when using decontroller. A low-pass filter is often placed after the decontroller. If you want to use decontroller, fine. Place a low-pass filter, for example, something like this, right after the decontroller. Because a low-pass filter is placed after the D controller. A low-pass filter is placed after the D controller because the derivative greatly amplifies the high-frequency noise. And the filter subtracts these unwanted high-frequency components while retaining useful derivative actions. Okay, that is common practice. But what is truly happening is I just don't want to use D controller. So the most popular controller in the industry is actually PI controller, all right? Because to use D controller, you have to design a low-pass filter. And how do I design the low-pass filter? How do I come up with the optimal design? It really depends on the nature of the noise. And the noise, being an uncertainty, is very difficult to predict. And even I do my best to predict the changing patterns of the noise, the randomness of the noise. Noise can vary with time. I may have to face different kinds of noise when my device ages, okay? When my device is being used in different environment or operated under different conditions. So if we have so many unpredictable uncertainties, let's just simplify the matters. Let's just get rid of derivative controller and try to use PI controller to the best, as much as we can. Okay. Now, we know derivative controller has trouble. How about integrator? Integrator, when it comes to the transfer function, it is actually 1 over S. By replacing X with J omega, this is what I will get. And by rewriting it as this, we know its magnitude is 1 over omega. And its amplitude spectrum, according to this result, actually look like this. And its phase spectrum is this. As you can see, an integrator suppresses high-frequency components of the input signals. Therefore, the negative effect of noise is not an issue for an integrator, for integral control. That is the reason why PI controller is very popular in real-world applications, because proportional controller and integral controllers are not sensitive to noises, okay? All right, again, let's go back to body diagram, okay? Let's check out the 4 basic forms of the transfer function and recall these slides, which explains why we want to use log function in the first place, okay? Now, the first factor is constant gain, K, all right? Now, what is K? K is a constant gain, okay? Now, if I increase the gain by a factor of K, what will happen to its decibel values? According to this result, gain increase, K increases 10 times, the decibel value increases 20, okay? So increase the gain in a way will elevate the amplitude spectrum of the system, right? Because I increase its decibel values. If I increase the gain, not just 10 times, let's say 100 times, in this case, where n equals to 2, then I will increase the decibel values by 40, okay? All right. This is K, and this is 20 log K, all right? The reason why it is a slope is a straight line. Log itself is not a straight line, all right? Is that for the horizontal axis, the numbers are not equally spaced, which means what I have here is actually log k. All right? Okay, now let's assume u is nothing but log omega. And let's take then minus 20 log become minus 20u. Okay, now here I want to compare the decibel values of two frequencies. Well, omega 2 is twice as large as omega 1. Okay, now when omega 2 is 10 times larger than omega 1, the difference between the decibel values as stated here is 20. However, is this difference is 2, all right? When omega doubles, its decibel values according to this result is actually 6 dB, okay, 6 decibels. Because if you times this by 20, what you will get is approximately 6 dB, all right? Now, remember that we want to consider these 4 basic forms of the transfer functions, of these 4 fundamental factors of a transfer function. So let's just go over them one by one, all right? Now, here, what we want to look at it is pole and zero at the origin, all right? Let's say I have a pole at the origin. If you take its decibel values, it is actually look like this, okay? So this is the amplitude spectrum on a body plot, and this is its phase. Now, it is nothing but a straight line with a slope of 20 dB per decade, all right? So it is, the amplitude spectrum is somehow very similar to a first order system. The only difference is that for a first order system, its amplitude spectrum can be actually broken into 2 parts. In the low frequency band, you actually have 0 dB output, okay? And this minus 20 dB per decade line will appear later after 1 over tau, okay, for a first order system, all right? Now, for 0, okay, h of x is equal to s, all right? And it is nothing but a differentiator. So its amplitude spectrum look like this. This is its phase spectrum, okay? So this line has a slope of 20 dB per decades. Now, those are poles and zeros located at the origin. Now, let's look into sample zeros and sample poles, which means let's first check out the sample zeros, which means 0 now is a real number, not just 0, all right? Now, again, we need to go to frequency domain. So we replace x by j omega. Now, we want to know its amplitude spectrum. So we take the magnitude of g and we know the angle, okay? Now, so again, similar to what we did before for the sample pole, we look at asymptotics for these sample zeros, okay? Now, to do that, we simply divide the frequency into 2 bands, 2 parts. One is the part that is much smaller than 1 over tau. The other is the part which is much higher than 1 over tau. And this is what we will get. And this is the resulting asymptotics of the amplitude spectrum of a sample zero. Okay, now we also did this derivation before for sample zero, whose asymptotics for the amplitude spectrum looks like this. So when we put them together, this is like a low-pass filtering. And by contrast, this is like a high-pass filtering operation. What do I mean by high pass? When I say high pass, I mean that high frequency components can easily pass this system, okay? Not just pass as the way it works. By passing through such a system, its high frequency components will actually be amplified, okay? And the degree of amplification is actually depends on or proportional to frequency, okay? Now, now if I plot them together, that is the body diagram, the amplitude spectrum of the body diagram of the sample 0 and the sample pulse. What I will have is these two curves, okay? Note that their pattern are similar. The only difference is that as omega increases, okay, the amplitude spectrum goes into opposite directions. All right, that's it. Okay, one high pass for sample 0, the other low pass for sample pulse. All right, keep that in mind. Now, let's come to the quadratic factors. Okay, remember these mathematical derivations. All right, now this is the transfunction of standard second order systems. After simple mathematical manipulations, I can rewrite it into such a quadratic form. Okay, now since I want to use body diagrams, therefore I take log and then times it by 20. Okay, the reason why I have a minus sign is this shouldn't appear in the denominator. All right, so the reason why we don't want to look at omega directly is that here, by looking at the ratio of omega over omega n, I can break, in analyzing the frequency response of the second order system, I can again break the frequency into two portions, okay? Entire frequency range into two parts. The first part is where omega is much smaller than omega n. If that is the case, then this becomes very, very small. This term becomes even smaller, okay? And by putting them next to 1, okay, what I have is I can ignore it. I can ignore it, okay? And this is the only term that remains. And of course, it gives us a value of 0 decibel, okay? However, if the frequency is very large, is very high, how high? Much higher than the natural frequency. Then compare this to this. This can be ignored. Let's say omega over omega n is 100, all right? This is 100, and this is 100, 1,000, 10,000, all right, okay? 100 compared to 10,000, of course, it can be ignored with very small inaccuracy introduced, all right? Similarly, this can be ignored. So the only term left when omega is much smaller, much larger than omega n is this. And this is what I have. So for such a quadratic factor, for such a standard second order system, my asymptotic curves actually consist of two parts. Well, the corner frequency or the turning point frequency or the critical frequency is located at omega n, right? For this part, that is for the low frequency band, what I have is 0 dB, which means the output, that when it comes to the amplitude of the output, it will be the same as the amplitude of the input. Why? Because the amplification ratio is 1, all right? When you times it by 1, it means nothing has been gained, nothing will lost, okay? It just stays the same, all right? But here, what we have is minus 40, okay? Minus 40, okay? Which means this slope, this line has a slope of minus 40 decibel per decade, right? Okay, here, for omega n, the dB value, the decibel value is 0, all right? This is, in here, omega is equal to 10 omega n, okay? So compared to this frequency, 10 times, the net frequency increased by a factor of 10. And if you compare its decibel value, it decreases by 40, all right? So this line apparently had a slope of 40 decibel per decade. Now you should have an idea about the order on the impact of this slope. If you have a first order system, then this slope, the slope of such a line is typically minus 20 dB per decade. But if you have a second order system, then the slope of this line will be minus 40 decibel per second. Minus 40 decibel per decade, per decade, okay? So the higher the order of the system is, the steeper the slope, this slope, okay? So the slope is pretty much minus 20 times n, where n is the order of the system, all right? Okay, now we can do similar things to the phase response, and this is what we will get, okay? Again, one additional parameters that we need to pay attention to is the damping ratio. Now, similar to what we saw before, here, again, what we have here is resonant peak, all right? And that resonant peak also depends only on the damping ratio. Now, why is Bode diagram useful? Let's check out this example. This example actually consists of 5 factors. The first factor is a constant gain, K, which is 5. The second is a pole at the origin, which is distant, okay? And the third factor is a pole located at omega equal 2, which is this. And then the fourth factor is a pole at omega equal to 10, which happens here. And finally, the fifth factor is this, which is a pair of complex conjugate pole at omega equal to omega to 50, right? Omega n here apparently is 50. So let's draw the asymptotics for each of these 5 factors, okay? This is for the first factor, constant gain. Why is it 40? Because 20 log 5 give you 40, not 40. And a pole at the origin apparently is this. Asymptotic is this, right? A minus 20 dB per decade straight line from the very beginning of the frequency, all right? And here, a pole at omega 0, which is the asymptotic of this first order system is this, right? Corner frequency occur is 2 radian per second. And the force factor is a 0, located at omega equal to 10, right? 10. Because it is 0, so it goes up. Finally, a pair of complex conjugates. So this is what I have. Omega n is 50, so the corner frequency is 50. And this slope, the slope of this line is, of course, minus 40 decibel, minus 40 dB per decade. And if you want to know the amplitude spectrum of this transfer function, all you need to do is add these 5 curves together. Okay, and it's not difficult to visualize the result. And here, we just plot them out. This solid line represents the approximate curve. The reason their approximation is here, what we have is asymptotics, not the real amplitude spectrums of these vectors. But since I take log, okay, since I take log, so I can add them together, and this is the result. By summing these 5 curves together, by adding these 5 curves together, okay? Because what we have here is addition. So adding them together is not difficult to visualize. Imagine if I don't take any log, I don't use body diagram. What I need to do is plot the amplitude spectrum of each of those components, and I have to multiply those curves together and to determine the final amplitude spectrums. Multiplying together, how do I imagine that? Okay, I can still do that, but it will be much, much more difficult than adding them together. Okay, 好，谢谢。And the solid line is asymptotic curves. The dotted line is the real amplitude spectrum. As you can see, we have a very good approximation. Okay, so another good thing is, if you don't like this amplitude spectrum, you want to change it, then you can use similar information. You know, if I for a certain frequency band, if I want to have higher, stronger response, maybe what I need to do is to add a 0 at, for example, this particular frequency. All right, because 0 will amplify, will enlarge the amplitude response. And if you think for this portion of the amplitude response, it is not weak enough, it's not small enough, then what you need to do is properly place additional first order system by choosing the right corner frequency. All right, you can do that because you have the framework of every factor, and you know the impact of those factors, because all you need to do is to add the body diagram into the original body diagram and try to imagine what will happen. Okay, and therefore such a tool is a very powerful design kit for controller engineering. All right, now I want to spend some time to talk about resonance frequency and resonant peak. The first thing is, how do I determine resonant peak for a second order system. Now, this is one way to represent the transfer function of a second order system. I already show you how do I come up with such a representation. All right. Now, since what our attention is now focusing on resonant peak, therefore, I need to determine the amplitude spectrum first. Now, this amplitude resonant peak occurs at the when this value, when this amplitude, this magnitude of G of J omega has a maximum, all right? Which means its that denominator at that particular frequency should have a minimum, all right? So let's just forget about the square root, because square root or not, it will not have any impact on the location of the minimum, all right? So inside this square root is this, okay? I want to find its minimum. What do I do? How do I do that? I take the derivative of G with respect to omega. And after taking the derivative of G with respect to omega, I set it to 0. By using this equality, I determine the value of omega. And that value happens to be this, okay? And this omega r is what we call resonant frequency. One thing is that that we need to pay attention to is that first, it is directly proportional to the natural frequency. So that the higher the natural frequency, the higher the resonant frequency. But it is also determined and influenced by the damping ratio. And you will have a maximum value only when eta is smaller than 707, all right? No resonant peak when the damping ratio is larger than 707, all right? As shown in these figures. This is the amplitude spectrums body diagram, the body diagram amplitude spectrums of a second order system. As you can see, as damping ratio becomes smaller, the resonant peak becomes more pronounced. However, when eta is larger than, say, 707, okay, which is this curve, you don't see any peak, all right, okay? So resonant peak only exists for underdamped system, but there are another precondition. That is, the damping ratio has to be smaller than 707, all right? Okay, so in that regard, probably one design specification is in order to avoid resonant peak. Maybe I should set out a specification. That is, maybe I should require my design to have a damping ratio larger than 707 to avoid resonant peak. All right? All right. Once I have this number, okay, I substitute this number into here, and then I can determine the maximum value of my amplitude spectrum, okay, and which turns out to be this. So it is a function of damping ratio and damping ratio only, all right? Now, again, for eta larger than 707, the resonant peak is 1, okay? Actually, there is no peak, all right? Now, if I plot it as a function of omega, all right? I just plot this equality out. It would look like this, okay? As eta increases, the resonant peak decreases. Now, recall that for a second order system, the state response has, for underdamped system, has an overshoot, and the percent overshoot, as we reviewed in the previous lecture, looks something like this. If I put this figure, if I combine this result with this result, and this is what I will get. This is for the resonant peak. This curve is for the percent of overshoot, okay? And they have one common similarity, that is they all decreases with damping ratio. So the plot shows how increasing damping ratio reduce both frequency domain resonance and time domain overshoot, reviewing the fundamental link between oscillations in the frequency response and overshoot in the state response. So there is always a close connection between the phenomenon we see in the frequency domain and time domain. After all, we are talking about the same system, okay? We just look into the system from different point of view, all right? But hope it will give us the same piece of information because we are looking at the same system. Okay, now, before we go any further to talk about the system spectrum, the frequency response of the system, I want to introduce first a method whose name is rule locus, to tell you one possible approach for controller design. Now, the first thing we need to clarify is what is rule locus. Rule locus. The rule locus method is a graphical technique used in control system to determine how the pulse of a closed-loop system varies as a parameters. Typically, the gain K changes. That is, here, we know the impacts of the location of the pole. You can move it upward or you can move it downward, okay? But how, let's say I'm designing a controller and there is one parameter I need to determine. And rule locus tell us how the location of the poles changes with the values of that parameter, okay? So I will have a good idea of how to determine the value for this parameter, which is typically a gain, okay? So it provides insight into the system stability and dynamic response, helping engineers design a controller effectively. So this is one tool to help us design controllers, because by varying the value of a parameter of the controller, we see how the locations of the pole changes, okay? And by placing poles at the different regions of the S-plane, we can get different dynamic response. It visually represents the relationship between system parameters and the pole locations, okay? Let's give you an example first, okay? These are simple examples to show that when I have different value of K, how the location of the pole will change. And these are the rule locus, okay? When you have different values of K, the poles will be placed at the different locations. If you choose the value of K too large, some of the poles will become unstable because it will go to the right-hand side of the X-plane. So the system will become asymptotically stable. It also tells you that with only one parameter, you cannot place your poles to whatever region you want. There are some limitations, okay? All right. So let's go back to the original remarks, okay? Engineers use rule locus to select game or design controllers to meet performance specifications such as overshoot, settling time, and damping ratios. Okay, as an engineer, I'm given some specifications. For example, your overshoot cannot be larger than 10%. Your settling time should be smaller than 1 second. Your damping ratio has to be smaller than, say, 0.8, larger than 0.8, things like that, okay? And to do that, rule locus might be helpful too. Now, this is a control system, okay? Here, this is G, this is H. This is in the main loop, okay? So this is, and we saw this was, we derived this result before. The transfer function of this feedback system, where this feedback system has C as its output and R as its input. So the transfer function of this closed loop system is this. Remember that as an open loop transfer function, as an open loop system, the original transfer function is G. This is a new transfer function. So let's say G of X is P of X over Q of X, okay? And G of X over P of X can be look something like this. So they will have different characteristic equation, which means they will have different poles. So one of the most important functions of closed loop feedback is I can change the characteristic equation, and therefore I can change the location of the poles, okay? And as a result, I can somehow modify or revise the dynamic response of the system, hopefully for the better, okay? Now, the rule locus method is based on the characteristic equation of closed loop system, which in this case, we assume there is one parameter that I need to consider, that is K, all right? Let me put it this way. Let's say I want to use a proportional controller, and the proportional controller is here, okay? Hey, now the next thing I need to do is to determine, to pick an appropriate value for K, for this proportional controller, all right? If if I add this proportional controller, then the transfer function will look something like this. Damn, where did it go? Okay. It will look something like this. Okay. And this will become my new characteristic equation. All right. So the rule locus method is based on the characteristic equation of a closed loop control system. Okay. Well, the value of K is a parameter whose value is weighted to be determined. Okay. Rearrange and isolate the open loop transfer function. Okay. Now, if this has to be true, then this has to be true. It has to be -1. Okay. This equation implies that for a point that lies on the rule locus, the open loop transfer function GH at the point must satisfy the magnitude and angle condition. Okay. Now, what are the magnitude and angle condition? The magnitude and angle condition, this has to be true, because when we talk about the poles come from the characteristic equations. Let's just assume, for the sake of illustration, G of H looks something like this. Well, there is a K left to be determined. All right. For this to be true, this part has to be -1, because 1 plus -1 is 0. For this to be true, remember, this is a complex function, a complex function whose independent variable is frequency, all right? Function function. Okay, G and H are not just numbers. They are functions of X. But since we are studying the system in the frequency domains, I've already said it many times. I had to replace X by J omega. Whatever the case, if this is true, no matter what S is, this has to be true. Okay, its magnitude has to be 1. And its phase or its angle, its angles has to be this, which means in the complex plane, okay, since this is -1, so it's located here. Therefore, its magnitude, which is the distance, which is the distance between this point and origin, is 1. Okay, now this is where the pole is. Now, and this angle has to be -1 H2 degree. All positive is also acceptable. All 40 degree. That is, I come here and then I go additional period, additional cycle. All right. So this is the reason why we have a 2K here. All right. Now, so the magnitude of JX must satisfy this. Okay. At each point of the rule locus, the product of the magnitude of G of X and K equals to 1. Okay. You can change the value of K, but whatever the value of K is, this has to be true. This condition helps determine the value K value for a specific point on the root locus. Okay. Okay. Now let's talk about the angle. Okay. The angle of GH must satisfy this equality. I already told you why this equality has to be true. This condition ensures that the argument, that is the phase of GH, matches the phase required for closed loop pole to satisfy the characteristic equation. All right? So this is what this equation what all about. Okay? For point S to be on a rule locus, if S has to be on a rule locus, as you can see, root corresponds to the root of the characteristic equations. So the root actually represents the location, the poles, okay? And rule locus actually represent the trajectory of the pole, okay? Why does it have a trajectory? Because if you change K, the pole will move to a different place. If you continuously change the value, okay, let's say from 0 to 100, okay, step by step, you see the poles varies from one location to the other location, okay? And if you connect all those locations together, it represents a trajectory, all right, okay? So for a point S to be on a rule locus, we have to sum the angle. Okay, now time. Well, I don't have enough time to fully describe what we need to say. So let's just call it a day. All right. All right. I hope you for the best. Okay. All right. And hopefully I will see you, all of you, next week. All right. Thank you.